Good to be with you once again for our discussion on rational functions. Let's just jump right in and see what a rational function is here. A rational function is the ratio of two polynomials where we've got to be careful that the denominator is not the zero polynomial. One of the things that you'll expect with rational functions is the idea of a vertical asymptote. Now, what is a vertical asymptote? Well, when a vertical asymptote pops up in a graph, we know a couple things are happening. We know that the y value is either going to positive infinity as it is in the two graphs here on the left, or it's going to negative infinity as it is in the two graphs on the right. You'll notice that we have some notation here that we've talked a little bit about already this semester. The y values approach infinity. That's what the little arrow means, approaches, as the x values approach a from the left. Here we go, a from the left, and the y values are approaching positive infinity. Here you see the x values are approaching a from the right as the y values go to infinity. Here the a values were approaching a from the left, and the y values are going to negative infinity. Here we approach a from the right as the y values go to negative infinity. So with vertical asymptotes, if we've got a vertical asymptote, folks, we are guaranteed that your function is either approaching positive or negative infinity, either coming in from the left or the right, or possibly both. We have vertical asymptotes. We also want to talk for a little bit about horizontal asymptotes. Now, there's one big difference between horizontal and vertical asymptotes. Graphs may cross a horizontal asymptote, but never a vertical asymptote. And this is because at vertical asymptotes, of course, our function is undefined. And just like we can predict the behavior of the graph around vertical asymptotes, we can do the same thing with horizontal. When a graph approaches an asymptote, folks, it's going to get real close to it. It's going to hug it. With a horizontal asymptote, it might actually cross it. We'll talk about how that works out here in a little while, whether we're going to cross a horizontal asymptote or not. There are some results that we can talk about with horizontal asymptotes. Notice here we've got the ratio of two polynomials. I've talked before about this notation. We've got two polynomials here. N is less than k. Now notice here my power of the numerator is n. That's the degree of my numerator. The degree of my denominator is k. And the degree of the numerator is less than the degree of the denominator. Anytime that's the case, then the x-axis, or the line y equals 0, serves as a horizontal asymptote. If the degree of the numerator and denominator happen to be the same, then your horizontal asymptote is y equal the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. And we know then x, as x approaches infinity or negative infinity, we know y is either going to infinity or negative infinity. Here we want to determine the horizontal asymptotes of each of the following graphs here. This is situation 1, where the degree of the denominator is less than the degree of the numerator. So y equals 0 is the degree of, or is the equation of our horizontal asymptote. With B, this is situation 2 as described above, where the degrees of the numerator and denominator are the same. Therefore, my horizontal asymptote is going to be y equal 3/2. And then, as you might have guessed, C here is describing situation 3, where the degree of the numerator is bigger than the degree of the denominator, and so we have no horizontal asymptote. I'm going to use HA as an abbreviation for horizontal asymptote a lot, so we can get used to that. So we're going to sketch our rational functions here, and we're going to do this without the aid of a calculator. So assume that f of x equal g of x over h of x, g of x and h of x are both polynomials, no common factor. We're going to find the x-intercepts. That is where the numerator is 0 we're going to find the real zeros of the denominator, and we're going to put in vertical asymptotes there. We're going to find the y-intercept, and then we're going to apply the theorem on horizontal asymptotes. Now, if there happens to be a horizontal asymptote, you have to figure out whether it intersects the graph or not. The x-coordinate of the points of intersection are the solutions of the equation f of x equals c. We'll see that in a little bit, and we'll plot those points when they exist. And then finally, sketch the graph of the function in each of the regions in the xy plane determined by vertical asymptotes in guideline 2. If necessary, use the sign of specific function values to tell whether the graph is above or below the x-axis or the horizontal asymptote. We may need to, what they're saying here, guys, we may need to look at test points back like we did in Unit 1 where we were solving inequalities. We might have to do the same thing here. Alright, so let's dive right in as we get ready to graph these horizontal asymptotes. We're going to try to take you slowly through this. First thing we're going to look for will be our x-intercept. Alright, we're going to look for that first, and so I need to know where is this numerator equal to 0, 4x equals 0 when x equals 0. Alright, so if x is 0, we've got the point 0, 0. Well, here we've got a bonus. This is the x-intercept and the y-intercept. This will save us some work. Alright, now let's consider our domain. Let's consider our domain here. We need to make sure that the denominator is not 0, so let me find out when it is 0 by setting the denominator equal to 0. 2x equals 5, that means x equals 5 halves. Alright, so my domain is all reals except for 5 halves, which means I have a horizontal asymptote at, I'm sorry, not a horizontal, but a vertical asymptote, my mistake. Anywhere the denominator is equal to 0, we have a horizontal asymptote. I have a vertical, let's say that again, let's say it right. Anywhere the denominator is equal to 0, I have a vertical asymptote. There we go. So I have a vertical asymptote at x equal 5 halves. And now let's think about any horizontal asymptote we might have here. Horizontal asymptote, well, degree of top equal degree of bottom. In other words, this is a first degree polynomial in the top. This is a first degree polynomial in the bottom. And so my horizontal asymptote is just the ratio of the leading coefficients. So my horizontal asymptote is y equal 2. And you say, well, how do we figure out whether we're going to cross that horizontal asymptote or not? Well, what we're going to do is we're going to set the function equal to the equation of our horizontal asymptote. So 2 equals 4x over 2x minus 5. And now we're going to solve that. So I'm going to solve that by multiplying both sides by the denominator. So 4x minus 10 equals 4x is negative 10 equals 0, which is not true. So what we have learned here, f will not cross the horizontal asymptote. F will not cross the horizontal asymptote. So let's see what we've got here. Let's come over here. We'll sketch this out. 1, 2, 3, 2, 3. Alright, let's get a different color going here. Red seems to show up well. So we've got an x and a y intercept right here at the origin. The domain is all reals except for 5/2. Well, 5/2, we know that that's 2.5. So we've got a vertical asymptote here at x equal 5/2. And then we said we've got a horizontal asymptote at y equal 2. Alright, so we'll label our asymptote. Now let's think, folks. We know that a graph, when it approaches a vertical asymptote, is either going to go to positive or negative infinity. Now this point then, as the graph comes over here, it's either going to go up or it's going to go down. But remember what we said a minute ago. Remember we said right down here that the function will not cross its horizontal asymptote, which means if it were to go straight up, it'd have to cross that horizontal asymptote. Therefore, we know what the graph is doing here. Alright, it's got to be going down. We also know that the graph has to hug and maybe cross. In this case, it's not going to cross. So we know the graph is going to hug our horizontal asymptote. Alright, and now we need to know what the function's doing over here. Well, we've got two choices. Our graph could either bend like this or it could act like this. All I really need to do is pick a test point in this region, and I need to see if that value is greater than 2. Now there's been a lot of times where we'd pick a test point and we didn't really care whether the outcome was positive, or we didn't really care about the value of the function at that test point. We just cared if it was positive or negative. Well, here we care whether it's bigger than 2 or not bigger than 2. So let's pick a test point. Pick x equal, I don't know, 3 sounds as good as any to me. Pick x equal 3. F of 3 equals 4 times 3 over 2 times 3 minus 5. Well, this is 12 over 6 minus 5, which is 1. So there's our graph. There's the graph of our function. Certainly, if you have questions about that, please bring those with you to class, and we'll be more than happy to discuss those. Alright, on to our next rational function here. Let's go back to black for a little bit, and let's figure out here, and let's try to go with the order that they present things in. It says find the x-intercepts. Alright, so x-intercepts, where is this numerator equal to 0? X plus 1 equals 0. That means x equal negative 1. So I've got an x-intercept at negative 1, 0. Then the next thing I'm going to look for, it says find the real zeros of the denominator. Well, where is the denominator equal to 0? X plus 3, x minus 1 equals 0, so x equals negative 3, x equal 1, and those are the equations of my vertical asymptotes. I've got vertical asymptotes at x equal negative 3 and x equal 1. And now we're going to look at our third thing here, find the y-intercept. So the y-intercept happens, of course, when x is 0. F of 0 equals 0 plus 1 over 0 squared plus 2 times 0 minus 3. So this is negative 1/3, so I've got a y-intercept at 0, negative 1/3. And then it says apply the theorem on horizontal asymptotes. Well, alrighty, the degree of the numerator is less than the degree of the denominator. In this case, that would be, let's check it out here, first degree numerator, second degree denominator. So 1 is less than 2. Thus, y equals 0 is the horizontal asymptote. Step 5 here, we want to see if the graph will cross that horizontal asymptote. So we're going to set our function equal to 0, x plus 1, over x squared plus 2x minus 3. Well, let's check this out, guys. We multiply both sides by the denominator here. We get 0 equal x plus 1. Hey, we've been down this road before. At x equal negative 1, we are going to cross. We are going to cross. Okay, so let's see here. And let's get, we know when x is negative 1. We know when x is negative 1, our y value is 0. So just a note, we cross the horizontal asymptote at negative 1, 0. Okay? So we take a look now at our graph. And again, let me change colors here for us. So we've got an x-intercept at negative 1, 0. We've got vertical asymptotes at x equal negative 3 and x equal 1. We've got a y-intercept at 0, negative 1/3. We've got a horizontal asymptote at y equals 0. So let's put that in. And we know that we are crossing the horizontal asymptote right here. So folks, that's the only place we can cross. And we know that as we get close to a vertical asymptote, we either have to go to negative infinity or positive infinity. And so we know what the graph is going to look like there in that region. Now the one thing that remains to be seen about this graph, if we look at guideline number 6, we're going to have to bring it into play because we don't really know what's going on over here to the left of x equal negative 3 or to the right of x equal 1. So let's check some things out here. Let's this is point number 6 to look at. Let x equal negative 4. Alright, so negative 4 plus 1 over negative 4 squared plus 2 times negative 4 minus 3. Well, this is negative 3 over 16 minus 8 minus 3. So what do we have? Negative 3 over 16 minus 11. 16 minus 11, of course, is 5. So this is easy enough. We know this entire region then is going to be less than 0. Alright. And we need to pick a test point over here to the right of x equal 1. So I'm going to let x equal 2. And really, guys, you might be thinking, well, hey, since all we care about is whether this thing is greater than or less than 0, couldn't we go ahead and make use of our factored form like we did back in Unit 1? And the answer to that is yes. So we could look at x plus 1 over x plus 3 times x minus 1. Alright, we let 2 go in here for x. This is going to give me a positive over a positive times a positive, which is going to be greater than 0. And I apologize here, I forgot I was drawing my graph in red. Let me take care of that. We'll make this red. as well. Hugging both asymptotes, and over here hugging both asymptotes. Alright, so there's the graph of f of x equal x plus 1 over x squared plus 2x minus 3. And of course, if you have questions, please bring those with you to class, and we'll be happy to talk about those. As we continue on, we'll take a look at our next example here. F of x equal x squared minus 3x minus 4 over x squared plus x minus 6. Alrighty, well, let's go to work here on our checklist. The first thing we're looking for is an x-intercept. So we need to figure out where that numerator equals 0. X-intercepts here. X squared minus 3x minus 4 equals 0. X minus 4, x plus 1 equals 0. That means at x equal 4 and x equal negative 1, we're going to have an x-intercept. Remember, please, intercepts are points on a graph, which means they are described using ordered pairs. So there's my x-intercepts. The second thing we're checking for are the real zeros in the denominator. So x squared plus x minus 6, where's that equal to 0? Well, this is x plus 3 times x minus 2. And so here, x equal negative 3 and x equal 2 are my vertical asymptotes. 3 says find the y-intercept if it exists. Well, okay. Y-intercept, we know we're looking at f of 0. 0 squared minus 3 times 0 minus 4 over 0 squared plus 0 minus 6. So we've got 2/3 here. So I've got a y-intercept of 0 2/3. The fourth thing our checklist has us look for is the theorem on horizontal asymptotes. And we'll notice here the degree of the numerator equals the degree of the denominator. And so they're both second degree polynomials. 2 equals 2, which means y equal 1 over 1, which is 1, is our horizontal asymptote. The next thing we need to check then is to see if in fact we cross the horizontal asymptote. So I'm going to set the equation of my horizontal asymptote equal to the equation of my function here. So I've got x squared minus 3x minus 4 over x squared plus x minus 6. Well, we can multiply both sides by x squared plus x minus 6, x squared minus 3x minus 4. Alright, well, my x squareds drop out. I'm going to move the x's over here to the left. So this is 4x equal 2, which means x equals 1/2. Now, we're going to cross the horizontal asymptote here. And I can get the corresponding y value by looking at f of 1/2. So I've got 1/2 squared minus 3 times 1/2 minus 4 over 1/2 squared plus 1/2 minus 6. Well, this is 1/4 minus 3/2 minus 4 over 1 divided by 1/4 plus 1/2 minus 6 over 1. Well, let's see what we get here. 1/4 minus 6/4 minus 16/4 all over 1/4 plus 2/4 minus 24/4. Negative 22 plus 1 is negative 21 over 4. And then 3 minus 24 is negative 21 over 4. Well, how about that? We're going to cross the horizontal asymptote at 1/2 1. And so, let's put this knowledge to work for us here. Let's draw out our graph. And let's see here. Alrighty, I've got x-intercepts at 4, 0 and negative 1, 0. I've got vertical asymptotes at negative 3 and at 2. I've got a y-intercept at 0, 2/3. Alrighty, that's right about there. And let's see, what else do we know? We've got a horizontal asymptote at y equal 1. So let's see if I can sketch this in here. And then I believe we decided that we're going to cross this horizontal asymptote at 1/2 1. Now, let me mention something. We went to the trouble to find out where the what the y value would be when x is 1/2. Okay, I did that this one time here to show you that the function evaluated at 1/2 is 1, and that makes sense. We're crossing this horizontal asymptote, right? Every point on this horizontal asymptote, every point has got a y value of 1. So let's see where we're at here. We are at, we said what? 1/2 1. So here I am at 1/2. Yeah, that's a little closer to 1 than I'd like. So let's adjust that just a bit. And we're still in red. Good deal. Alright, 1/2 1. There we go. Alrighty, so we're crossing our horizontal asymptote there. Now we know quite a bit. We know that if this thing is approaching this vertical asymptote over here, it's got to be going down, because the only place it can cross this electric fence, this horizontal asymptote, is right over here. Okay, so it's bending up like that. We know here that the graph has to be going close to that horizontal asymptote, and over here it's got to be bending down and getting close to the vertical asymptote. So the only thing that really remains to be seen is what's going on with the graph over here to the left of x equal negative 3. Well, let's check this out here. This is actually 6 that we're looking at. I'm going to let x equal negative 4. And so what do I have here? F of negative 4 equals negative 4 squared minus 3 times negative 4 minus 4 over negative 4 squared plus a negative 4 minus 6. Alright, 16 plus 12 minus 4 all over 16 minus 4 minus 6. 28 minus 4 is 24. 16 minus 10 is 6. This is 4. So we are above the line y equal 1. And we know then, folks, that our graph, it's got to hug the horizontal asymptote as x goes to negative infinity. And it's got to hug this vertical asymptote as x gets close to negative 3. And so here's a sketch of this particular function. And as always, bring your questions into class. We'll be happy to look at them. Now we've got an additional topic here that we want to look at in this section. And this is the idea of the oblique, or the slant asymptote and how it plays in. An oblique or a slant asymptote for a graph is the line y equal ax plus b with a not equal to 0, such that the graph approaches this line as x goes to infinity or negative infinity. If the graph is a line, we'll consider it to be its own asymptote. If the rational function f of x equal g of x over h of x for polynomials g and h, and if the degree of g is 1 greater than the degree of h, in other words, the degree of the numerator is 1 more than the degree of the denominator, then the graph of f has an oblique asymptote. To find the oblique asymptote, we're going to use long division to find the equation of this particular of the particular oblique asymptote that we're looking at. Okay, so let's see what's going on here. Find the oblique asymptote and sketch the graph of f of x, or of f of x. Determine the other key points that we have discussed. Alright, so let's go back to our checklist here. We're going to start, I'm going to get me my black ink back here. We're going to start out by looking for the x-intercepts. Okay, and so I need to know where this numerator equals 0. X cubed plus 1 equals 0. Well, let's factor. X plus 1, x squared minus x plus 1 equals 0. Now guys, hopefully you've got enough experience with this by now. We know that x equal negative 1 is going to be a solution, and if we check the discriminant of this thing, b squared minus 4ac, alright, negative 1 squared minus 4 times 1 times 1, this thing's less than 0, and therefore there are no real solutions coming from this part. So we've got an x-intercept at negative 1, 0. Alright. Then we need to know where the denominator is equal to 0. So I'm looking here for the places where x squared minus 9 equals 0. Of course, we can factor this. X plus 3, x minus 3 equals 0. X equal negative 3. X equal positive 3. So these are my vertical asymptotes. And then for 3, I need to find the y-intercept if it exists. Well, let's see here. F of 0 in this case is going to be 0 cubed plus 1 over 0 squared minus 9. So this is negative 1/9. Alright, so that's going to be my y-intercept. And now the next step we usually look at would be the horizontal asymptotes, but note here, degree of the numerator is 1 more than the degree of the denominator. Thus, we have an oblique asymptote. And from here on out, I'm going to write that as OA for oblique asymptote. So we need to find the equation of that. We're going to do that by a little polynomial division here. You remember this. X cubed plus 0x squared plus 0x plus 1 divided by x squared minus 9. Alright, so we know x cubed divided by x squared is simply x. This gives me an x cubed minus 9x. You'll remember we need to subtract, which causes me to change the signs. Leaves me with a remainder of 9x plus 1. Okay, so the equation of my oblique asymptote here, or my slant asymptote as some like to call it, is y equal x. So I've got an oblique asymptote at y equal x. Alrighty, so let's get ready to graph this thing here. And what do I know? Well, I know that I've been graphing in red ink, so let's go get that red one more time. And let's see, we've got an x-intercept at -1, 0. We've got vertical asymptotes at x equal -3. And at x equal 3. Exciting stuff here. What else do we know? Well, we've got a y-intercept at 0, -1/9. So right here below the origin is a y-intercept. And then we said we had a slant asymptote y equal x. Now, something that I didn't mention, okay, it is possible to cross oblique asymptotes as well. Now we might make note that the equation of our oblique asymptote is y equal x. Okay, so with that in mind, we are going to take the equation of our function, and let me slide back to black for this just for a bit. We're going to take the equation here of our polynomial, or I'm sorry, of our rational function, x cubed plus 1 over x squared minus 9. We're going to set that equal to x, and we're going to solve this equation. So x cubed plus 1 equals x cubed minus 9x. 1 equals -9x. X equals -1/9. Alright, so if x is -1/9, we know then that y will be -1/9 as well. And so let's put that in right in here. And while I'm at it, let me draw in this slant asymptote. Y equal x. Now, we can tell that we're crossing right through here, and I've got to move on up here because the only place I can cross this slant asymptote is right there. So this has to go up. This has to come on over here and go down. Alright, now the only thing we need to figure out is this side. Does it do a little U right here, or does it bend like this? Likewise over here, do we have a bent up thing like this, or do we have the little U here? So I don't know. Let's we're running out of room here a little bit, but this is actually still step number 6. Let's pick f of 4. All right, 4 cubed plus 1 over 4 squared minus 9. Well, 4 cubed is 64 plus 1. 65 over 16 minus 9, well, that's 7. Well, we know that that's going to be up here. So I can switch to red and trace that in, a little bendy there. And let's come over here and check to the left of -3. So once again, f of, let's say, -4 will work. So we've got -4 cubed plus 1 over -4 squared minus 9. This is going to be -64 plus 1 is -63 over 16 minus 9, which is 7. That's -9, so we are below both of the asymptotes, below and to the left. We're going to have a little bend right like that, and there's the graph of x cubed plus 1 over x squared minus 9. And with that, we have concluded lesson 3.5. You guys know what class discussion problems to look at, what problems to look at for homework. Please go through those, and certainly if you have questions, bring those up in class.